that's useful. Okay. Stop.
Is that a bit dramatic?
That's okay.
Yeah, that's okay.
So there isn't much to say, except for, if you didn't know yet, tonight at 6 there is a reception. 7. Tonight at 7 there is a reception. Not here, but in the computer science department, which is not far away. It's like 5 minutes walk. And otherwise, there's nothing much to say. Like, you do whatever you want.
Welcome everybody to the spring school, you could say that.
Okay, yeah, usually. So, okay, right, so there's going to be a series of lectures by several people, and I start off the first one, which is in, which will be by 2 speakers, myself and Aleks Kissinger, who's sitting there with a big beer. And I'll do the first 2 hours, they'll do the second 2 hours. And basically what we're going to present here is what we have been writing down in a textbook, which is called Pictures in Quantum Processes, which we would have hoped to have been finished and published by now, and which is nowhere near. So unfortunately there is no finished set of lecture notes, or maybe in the next 3 days we can write 100 pages, then we should be okay. But this probably is not going to happen. But we will try to publicize things as soon as possible. We expect that everything is finished in a month. Anyway, so that's it. This basically started, this is basically what here in Oxford is, in the computer science is now taught as the quantum computing course. So the whole point of this book and this series of lectures is to teach you quantum computing, quantum foundations, quantum theory in general, but just purely diagrammatically. We're going to go all the way to quantum algorithms and things like that, but it's going to be done completely diagrammatically. And the point of doing so is showing that this is possible. Then in the other talks, especially by Jamie Vickery and Chris Heunen, you will kind of see what the mathematical backbone is behind the scene, which is category theory. But I won't mention category theory at all. The whole idea is like to present things you don't need, to build things, it's useful. Right, so this is like an overview of the chapter, it doesn't really matter, so I'll do the first 6 parts, probably the first 3 in this hour. And so the first thing we're going to introduce is the idea of processes as diagram. So while presenting quantum theory diagrammatically is like, of course, a changing format instead of like linear symbolic formula, you see diagrams, but it's also kind of a change in philosophy and a change in perspective, because rather than one would usually think in terms of, when one is doing physics, thinking in terms of the state of a system as the main thing, it will be processes now which will be the main thing, with state just as a special case of a process. So how does this work? So basically we will represent a process by a box and a system by a wire. So this is like a typical physical process, like a beam splitter, which you have on an optical tail or so. And so you've got a physical system coming in, which is a photon, and then, for example, you've got 2 systems coming out, which are 2 photons. Now, something which is, so this is the language. This is sort of the most primitive level of language. You've got a system which you represent by a box. No, you've got a process which you represent by a box, and then you've got inputs and outputs which represent the physical system. Now there's already conceptually something interesting happening here, because for a very long time, almost 100 years, well, say 80 years, people have tried to axiomatize quantum mechanics in other ways than Hilbert space, which is the usual description due to von Neumann. And actually it was von Neumann who started this quest for an alternative way of doing quantum mechanics. And part of this is called quantum logic, and historically the big failure of that field is it couldn't deal with compound systems, composite systems in like an elegant way. On the other hand, very early on, Schrödinger has always said, like if you want to understand quantum mechanics, we understand compound systems. That's the essence. While people like von Neumann thought quantum measurement is the essence. So no, it's composite systems. And what you see here, at this most basic level of language, is we got 2 photons coming out. So at this very basic level of language, we're already considering multiple systems before we say anything else. So it's sort of a big departure from all other axiomatic approaches which have been developed in the previous century. Now, the thing is, this language is of course very general. Like, it can also apply to computer programs. Like you got here a computer program, quicksort, and then you got something, the system coming in as a list, and systems coming out as sorted lists, if it works properly. So you can be, at this early day, you don't have breakfast yet, so this is how you do it. You take egg, you take bacon, you cook it, and you get breakfast. I failed to do this morning. And then you got processes like this, which, I don't know, not for commercial exploitation. Stick stuff in and you get not very useful stuff out. Here's a mathematical process, so thinking more abstractly. You got two real numbers coming in, you got a real number coming out. So these are all ideas of processes. So that's the basic element of the language which we are going to use. And then the idea, so in a mathematical structure you've got your elements, so your objects of your structure, which are here these processes, and then you've got operations on these things. And here the operations will be composing. So you will try to compose these processes, and then you end up with something like this. And this is what we call a diagram. So you've got the number of processes here, 3, there's a number of systems involved. The system can occur at several different places, right? And the thing is that the fact that you got different systems involved makes that you have to be a little bit careful when you compose them. For example, if you want to compose these processes, they can't just be composed in any old way. Like here you see a D, there you see a D, so you could stick this thing in front here. Here you see an A, there you see an A, so you could stick this thing up there. But there are of course things you're not allowed to do. So these are the two things I described. But you're not allowed to do this here. And this of course is the very essence of mathematically how you end up with doing something like category theory. Like the idea that there are different types, some of which you can compose and some of which you can't. It's like the idea of a category. So here you can see why category theory sort of one way or another comes in here in describing these sort of pictures. Now, so here is a more concrete example, which people travel from other countries here to do PhDs and postdocs and stuff like that. You know, like you have the plug strips and then you need all these adapters because things don't match. And the idea of the diagram is like such a diagram which would look like this, is then kind of a representation of what in reality looks like this, right? So you've got a plug strip here, so a plug strip, you've got 3 outputs, which are 3 wires. Then here is the adapter, there what you do drill. So this is the basic idea of a diagram. Okay, now the idea is that these diagrams represent something which we call process theories. So what is a process theory? It's sort of, it occurs anywhere. Basically it consists of a bunch of systems which you could give a name S, and a bunch of processes, and each of these processes has a number of inputs and outputs. And that's exactly what we've been seeing. Now sort of what is the real content? The real content of such a theory? Well, first of all, you want it to be closed on the plugging. That's the kind of operation you have. So if you plug these together, it still should be a valid process. Okay, if you look at diagrams just like that, you can just plug them together and make big diagrams of smaller diagrams, but sometimes it will happen that different diagrams are actually equal, just because of the meaning of the processes inside, right? An idea, if like a diagram, if the process would be a rotation in physical space, and you rotate 180 degrees, and then you rotate again 180 degrees, it's the same as doing nothing. And this comes from the content of the process by saying what it is. It means rotating 180 degrees. So one of the things is that such a process theory should tell us is like how to interpret the boxes in the wire, and consequently when 2 diagrams are equal. This is like the content of what you would call a process theory. And for example, in the case of quicksort, so concretely, okay, we have a box with quicksort written on it, but this is what we mean, like a certain program, right? And if you then do this program twice, then you know it does the same as doing it once, because if it works properly, your list is sorted, so you don't have to sort it anymore. Yeah. example, for example, is if you see a mathematical expression like this, then you really think of a function which we represent here by the graph. And then you can write down equations in terms of your boxes too. You know, like negative of negative is identity, for example. This idea is fairly easy. Now, so a remarkable thing is when you do these diagrams is that a lot of people, and even a lot of pure mathematicians, are very suspicious about them. They have a very hard time thinking of them as real mathematics. Well, they're proper mathematics, and there's like supporting theorems which related to symbolic mathematics. Therefore, like, it's sometimes useful to just write them down as symbols. Then people say, ah, yeah, now we believe in them. And like, so here you see this process, and here you see, which is called FE. We write down an F, and we just write down ABC as these subscripts, and then BD as subscripts. And when you already see that things become a little bit like uglier, because we got a B as input and a B as output, so we kind of have to distinguish them here. There's two B's going on. And in fact, the way this worked historically is Penrose is from here. He had to deal with these things, with this tensor rotation, and he hated it because it's just hard to read. And he started to write this down as this. So that's how it worked historically. First there was this, and then there was this. Things become particularly hard to read if you go something like this. It's obviously immediately clear what he does if you see that. And here it becomes a little bit of a mess. What you do is you see an A2 here and an A2 here, which then means F as an output which is called A and which feeds into G. Yeah, it's this one. So you can write things down symbolically, and you can. But at the symbolic side, you have to do a little bit of bureaucracy to be careful. For example, if you want to write an identity somewhere, then one has to come up with a little trick and stuff like that. So, but one can establish a perfect correspondence between this sort of old tensor notation and this diagram. So this makes you maybe feel more comfortable with the fact that we're actually dealing with proper mathematical expressions here. Right. So now, once you have diagrams, you can actually see what's the algebraic structure of diagrams, and that's actually how you end up with defining something like what we'll see later is a monoidal category, because monoidal category is actually obtained when you start composing these diagrams together. And there's two natural ways of composing them. If you really think of these diagrams as processes, then you can think we do this process while we do the other process. And we use the word while, and the notation we use is tensor. You see, it's kind of interesting that the tensor symbol already is still very present at this very abstract level. Well, I wouldn't say abstract, it's just very general, not abstract. So at this very general level, this tensor system is already present, and it just basically means you take a diagram and you put it side by side with another diagram. That's what it does. That's all. That's what it does. Nothing more. And then another composition operation would be after you have a process. You have a process, this one, and you do this after this one. Like a big constraint, of course, is that these things should match with these things. They should match up, otherwise you can't do this. And that's what people refer to in computer science as types. Types match this. Anyway, so we got these two compositions, while and after, and then, so you got a structure, but you can treat this as a mathematical structure with these two compositions, and you can check that these operations are associative. They have respective units, like the unit, for example. Units are kind of cute in this case, because the unit here, unit for this operation is what diagram do I have to put here, such that what comes here is this one. What do I have to put here? What is the thing you put next to something and it doesn't change it? Well, nothing. The empty diagram. The empty diagram is the unit for this operation. Empty diagram doesn't mean anything like 0, it means something like 1 multiplicatively. So you could have an equation where on the right hand side you have nothing. For example, the expression that something is normalized equal to 1 would have an empty right hand side. Okay. So it's a kind of nice notion of units. So on the other hand, what do you have to stick? What do you have to stick here in order to get this thing back? So just two pieces of wire. They don't change anything. They don't change anything. So identity type of wires will be the unit for this. So we end up with this sort of structure, and then you can basically this ends up being a strict monodal category if you work with it. And the main reason we introduce these operations is to identify a certain type of diagram, which we for now call circuits, and then because in quantum information people call these sort of things circuits, but anywhere else in the world people don't call this circuits. So okay, just a name. So what do we mean by a circuit? A circuit is something which we can build by means of these two operations. So it's a process we build by doing things in parallel or sequential, side by side, one after the other. Anything you build like that, you would call a circuit. It's just a name circuit, you know. And then you can prove easily that a circuit would be the same as saying that there is no box above itself. So you start with a box, and you go further, there's nothing above itself. And then the corollary is that to such a circuit you can sort of assign a flow of time. So here you got the past, there you got the future, and you can think of time flowing through the boxes. So this is one kind of diagram. In category theory terms, this would be like a symmetric monodal category you get here in this way. Now, you'll see this later, but so this is not an example of one, because like this box is above itself, because if we go out, we find it again. So this would not be an example of such a circuit. Now the circuits are the most interesting ones. The whole point is we're going to look to other kind of diagrams which are more interesting. That's the main point here. But this is an important sort of basic level of the most trivial thing you can have. Well, not trivial, but the sort of most basic structure you would imagine. Right, now, we showed before that diagrams can be represented symbolically with in terms of distance notations. And if you go to the literature, people writing about these diagrams and proving theorems, they would always use monodal categories, symmetric monodal categories, like they are basically category theory papers. So since we can do things symbolically, why do we want diagrams? Well, I already sort of hinted that it's more intuitive, but can you sort of, the question is, can you actually, in a more crisp way, say that it's actually better? Even purely mathematical, right? Is there a way in which diagrams are better? And basically, okay, that's what I just said, like since we can define circuits symbolically, why bother with diagrams? The thing is, you get equations for free. What does it mean to get equations for free? Well, I'll show you what it means. It means some equations are just implicit in the notation. Here is like a very simple example. Right? You would typically in the symbolic mathematics you would have to say that this stencil is associative, which means saying that this thing is equal to this thing. Now, if you write the diagram, then you just write this. You're not going to put brackets here. You just don't do it. We didn't do that, right? We didn't introduce the concept of brackets in diagrams. Because you would not do it. It's stupid. It would be stupid. It's bureaucracy for no reason. But actually this means that in this symbolic notation there is a piece of bureaucracy which is just not necessary really, which is redundant. So here is so associativity equation is something you have to carry around in symbolic notation and which you don't need in diagrams. Here is another one, like saying that the empty diagram is a unit first requires a notation for the empty diagram, for example, something like this, one, whatever. And then you have to say that this is equal to that. Now, in diagrams, these two equations are just the same. There's no way to write this down other than this. You put a diagram side by side with the empty diagram. Now, okay, these are the easy ones. These are the sort of, you could say, yeah, okay, whatever. So let's go to a more interesting one. So now, here you got an equation. See, there is a tensor symbol, there is a tensor symbol, here's a tensor symbol in the middle. Here you got a composition symbol, a composition symbol, a composition symbol in the middle, and these things are a little bit messed about. So this definitely is not an on-the-nose identity. There are two different formal expressions. But let's write them down in language of diagrams. So first, take this one. So we have to put this side besides this, and we have to put this besides this, which is basically just dropping dropping the tensor notation, we drop the tensor notation, and then the left hand side has to go on top of the right hand side, and we get this. Now we look at this expression. This was the other expression. So we have to put this behind this. We have to put this behind this. We get this. And then we just drop the tensor symbol. And we get this. Have a look. We go back. Have a look. It's the same. Right? It's the same. So two completely different symbolic expressions become the same diagram. And now the thing what you need to do is, if you want to, so I'm not going to insist further on this because the question just doesn't arise when you're doing diagrams, but if you formalize things in terms of category theories and complete mathematical models, then you actually have to specify all these equations and check them for a particular model. And if you never open the book on category theory or something, then you should open a book, for example, Maclean, which is like one of the fathers of category theory, and you look for a definition of a monoidal category. And I would say, without any background in category theory, to get to the point that you can read the definition would take you, I guess, no category theory background, reading the definition of a monoidal category in Maclean. A year?
A month.
A month? A month? Okay, a month.
3 hours a day.
Okay, okay. He's a smart guy. He's a smart guy. But anyway, so while here we just said diagram, it would take you a month just to work through the symbolic definition, and because then you would read that the type of equations that I down here, there's actually an infinite number of them. Similar equations, and then you can prove theorems which show actually you can do it with a finite number. But that's how. So it's and the guilty one there is essentially set theory. Set theory makes things like really. Set theory requires a lot of bureaucracy to formulate the idea of a diagram. It requires really a lot of this sort of bureaucracy with brackets. Now, fundamentally, if you look at this diagram, what is important is that it's written down in 2 dimensions. You've got a dimension from bottom to top, which we say is after, and you can interpret in terms of time. First this thing happens, and then you've got this dimension, which, well, you could sort of think a little bit of a space. Like one system here, another system there. Or in a way it's more systems, like different systems, but you can think a little bit of space. So you've got a fundamentally 2-dimensional thing going on here. And one composition, the after, goes in time, while the tensor goes in space. And the reason why things become so complicated, like that you end up with 2 expressions which actually come down to the same diagram, which don't, is because you're trying to write something which is fundamentally 2-dimensional in 1 dimension, on 1 line. And it's just hard. If you have any picture and you want to tell in 1 line what it is, you completely lose any intuition or whatever to deal with it, and you need to come up with a protocol with lots of rules and stuff like that, how to do that, going from 2 dimensions to 1 dimension. Because there's no natural way to do that. You have to come up with some procedure which involves a lot of rules which you have to choose, which are by no way natural or something like that. So it's just very good. So by trying to push something fundamentally 2-dimensional like this in 1 dimension, you have to do a hell of a lot of bureaucracy, and you have to invent it actually. You have to invent bureaucracy to do that. So why would you do that? It sounds very stupid. Why would you do bureaucracy for the sake of doing bureaucracy? It's stupid. Right? Anyway, so now we have this idea of a diagram, and we convinced ourselves that it's good to do that. So we can now talk about some very special diagrams. One example would be a state. A state is a diagram where you have no input and an output. It's like, physically you would think of a preparation procedure. In computer science terms, it's like your computer is initialized in that way. This is the state of your hard disk. This is what the content, this is your memory. You don't really care how it got there. So you know that in your computer there is a certain movie that you want to watch. Okay, you're happy it's there. You don't really care whether somebody bought it or he actually stole it or hacked it. You can watch it, you know. So the same with say, a piece of food, like if you got a potato, you don't want to know the name of the farmer who sort of grew it. You don't care. This means there is no input. You don't really care where it came from, right? You just care that you can actually, well, cook it and eat it. Right? So a state means you got something available and you can start acting on it. Start acting on it is like the output variable. So that's that. So it's a special state. Is just a special process now without inputs. So effect or test, if you want to, it's kind of the dual. It means you got an input but you got no output. Sort of the most easy example is you discard something. You got something and you forget, but it's not very useful. Well, it's kind of, people who know quantum information know that it's kind of useful too. But so you got something and you discard it. So a test is kind of a special case of an effect. It's basically you check your computer and you conclude whether something is in it or not. If it's not in it, so you discard. So it's sort of, you will see examples, but it's obviously diagrammatically what it is. It's something with an input without an output. And then you got, of course, if you compose something with an output without an input, if it's something with an input without an output, you get something without an input and without an output. And that's what we call a number. And basically, what it will represent for us most of the time will be something like a probability. A probability is not something you can put an input in or an output. It's just there. It's sort of a global property of a picture which says with which likeliness it may have happened or something like that. We'll see later how it happens. Now, of course, something like this without an input and an output has a lot of freedom with the diagram. You can just move around. It doesn't really matter where you write it because it doesn't connect to anything anyway. Well, the really cute thing at this level is we can already write down a Born rule. Just for any kind of diagram, we can define something which is a Born rule, and which means whenever you have a state and you compose it with a test, the number which we get out we call probability. This is actually a Born rule. When in quantum mechanics people talk about the Born rule, this is a Born rule. And this will be for us the only thing we care about. If a state means in effect, we get a probability. That's actually now going beyond what diagrams tell you. This is like something we actually now want as some kind of interpretation from it. If you see something without an input and an output, we want to think of it as a probability. It could be different. It's not necessary, because if you would build the diagrams, if this would be like, if your process would be complex matrices like you use in linear algebra, complex linear algebra, then this would not in general be a probability, but a complex number. So this is not the case we really don't want. We'll see some examples like that, but in the end we don't really want things like that. So this is not like take a vector, a cat and a bra, and you get a complex amplitude. We don't want this as real. We don't think of this as physical processes. This is just maths. This is just maths. This is not physics. So for the physics, we want these numbers to be probabilities, and we can make it work. Now, nonetheless, you've seen these kind of things, because if you take a triangle like this and we rotate it a little bit, and then we do some cutting, then you get what is called a cat in quantum mechanics, right? And if you take this triangle, you rotate it a bit, then you come what's called a bra. And then this sort of, what I was just talking about, gives you a bracket. So basically, this notation is like a two-dimensional extension of Dirac notation. So you already get the benefits of Dirac notation built in automatically, but you do a lot more, exactly what I was just arguing. This fundament. So if you start writing down things which people talk a lot about in quantum information type, if you would teach in quantum information course something like entanglement swapping, and you try to write this down in proper old-fashioned Dirac notation, you basically can't do it. You can't do it. Or you have to sort of rely on bases and explicit, but you can't do it. Because it doesn't want to fit on one line. It's a fundamentally two. So you could actually ask yourself, why didn't Dirac come up with two-dimensional language? It's so natural to do it from that point of view. And my guess is like it's pure technology. How do you write a book with a typewriter? It has to be on a line. I think a lot of previous century mathematics has been dictated by the fact that we use typewriters to write with papers, and so things have to be linear. And then of course there are like the Bourbaki bastards who told you should write diagrams and you shouldn't use examples and you should be purely symbolically and don't think about things. And So they had a bad influence too, at least on the continent where I'm from. Maybe the English here, they escaped from their good old hatred against the French. And anyway. Right. Right. Okay, so now, once we have this diagrammatic language, we can start with, the nice thing we can do now is make general definitions which apply to many things at the same time. And so, for example, and you can, some words, like a word like separable gets a very nice meaning. Separable really means separating, disconnected. So a box would be separable if it consists of two boxes. Which means if you've got a process here, with an input on the left, an input on the right, an output on the left, an output on the right, you can actually disconnect it in two separate independent processes which don't interact. So disconnected really means no interaction. So the whole paradigm here is if you see a wire, it means something is talking to something. If you see no wire, they live independently from each other. So this would be separate. And then you can specialize this definition like to what you would call like separable states. Like just for those people who know quantum information, I have to say pure state here, separable pure state. So you got a byproduct state, and actually you can describe. So this is like the fundamental, like in category theory terms, this is like Cartesian. This means Cartesian. You can describe something by describing the parts. That would be Cartesian. And so this arises if you don't have any inputs here. If on the other hand we kill this input and that output, then we get this definition. And this would be a separable process. So what this means here is that whatever comes out of F kind of only depends on psi, because there's no connection from this bottom to the top. So the only thing which this could add, say, is a probability, but like you would have a constant process. This would be a constant. So you get a constant. So this would be like a rank 1 projector, for example. A rank 1 projector would be something like that, which arises as a cat graph. So okay, now the reason we write down separable, and I use the word Cartesian, is because the really interesting stuff happens when things are not separable anymore. That's when the really interesting things happen. And rather than saying, okay, we got a theory in which there is stuff which is non-separable, we will be trying to make this, say this a little bit nicer, just by relaxing our notion of diagram in a sort of funny way. And then actually there, automatically we will get non-separability built in. Right, so I already mentioned this is the Schrödinger quote from 35. So what we're going to do now is we're going to introduce a wilder kind of diagram, and implicitly we will get like non-separability from this wild kind of diagram. To show this, I want to explain sort of what is at the core of this special kind of diagrams in still a little bit more like a defined way. So let's go back just a little bit. So you see, separation for a state means the state consists of two parts. Separation for a process means the process consists of two parts. Now, is there a way we can? So these are very stupid processes, yeah. It's very like there's not many interesting theories which would only consist of things like this, constant process. Can't do anything. Suppose your theory is completely consisting of constant process. It's stupid. Well, there are theories which always have this property, like if you talk about sets and functions, like if you take sets as your wires and functions as your boxes, then you get something like this, because it's a Cartesian theory actually. Well, it's not totally uninteresting. Sets are not completely uninteresting. Many people have devoted their life to studying sets and functions, so not totally uninteresting. So an interesting theory would have like non-trivial, any interesting theory which you can imagine would have processes where this is not the case, right? Is there any way we can relate this to this, saying that having non-trivial processes means having non-trivial states in the same disconnect? And that's something people in quantum information know as Choi-Jablonkovsky, which relates bipartite states to bipartite processes. And let's see how Choi-Jablonkovsky, which people learn from quantum information, some of you, looks in terms of diagrams. Well, Choi-Jablonkovsky basically tells you, if you've got a process with an input and an output, how do you transform this into two-system state? Now, the way to do this is to pick a very special state. So this is a very special state, we denote it by a cup. And if you apply a process to one side, then you kind of get a two-system state which maybe encodes that process. Maybe we have to put some requirements on this special state in order that it would be the case. Like physically, you would think of this as if you know what a Bell state is, as a Bell state, and you apply a process on one side, and then you hope that then the process is encoded as a two-system state. Okay. So this is the sort of map which would translate a process to a state. Now how can you build a map which takes two-system state and turns it into a process, which means one input and one output? Well, this is the way to do it, right? You take one input and then you stick this thing in, like that, and you see as a result you got one input and one output. Now, in order that this is like proper encoding, these two maps should be each other's inverses. You want these maps to be each other inverse so that you can go from a process to a state, to a system, and then from a two-system state back to the original process. And it turns out, to achieve this, that you need these two equations. You need these two equations to achieve going from a two-system state to a two-system process, a two-system process. and you would hope that if you got a property or a special state like this and a special effect like that, that your non-trivial processes would, well, your non-separable processes would result in non-separable states. And then you're in business with an interesting theory. So if you can impose this on a theory, you maybe get an interesting theory. Now I'll just quickly show that these equations are enough to establish that these are each other's inverse. I'll show this now. Okay. So we start with the process. We apply this map. Which means we stick a state inside. Then we apply the other map, which is we stick an effect there. That was the other. So this was from process to state. This is again from state to process. And now you see, if we use this equation, I'll go to the previous page. We end back where we started. If we use this A equation, then we end back where we started, right? So that's a good thing. And similarly, if we start with state, and then we apply this effect here, and then this one to turn it back into a state. Yes, but this equation, the other previous page, that gives you a state. So like having a process theory in which you got a special state, this one, and a special effect, this one, which satisfy these equations, it then follows that this map and this map are mutual inverses. So they allow you to go from a two-system state to a process, and from a process to a two-system state. And then you would expect that if you got interesting non-separable processes, you will have non-separable states too. Right? This is easy to show actually. Okay, so that would be a good sort of place to start looking for interesting theories where you got non-separable states. But we can actually make the situation a little bit nicer. Instead of denoting this state like we did, we will actually now just denote it by a little cup. And instead of denoting this state like we did, we will denote it like a little cap. And then look at the bottom equation there. This becomes this. And suddenly, what looked like a pretty ad hoc equation here, this one, pretty ad hoc thing, becomes something very stupid, well not stupid, but very clever, but very simple. Basically what you got is like you got a piece of wire here, you got a piece of wire with an input and an output, piece of wire with an input and an output, piece of wire with an input and an output, just a piece of wire in three cases, from input to output. If you think about that, it is like completely trivial equations. And you can really think in terms of physical wires, like electricity wires. Yeah, it doesn't really matter that it does this. You got an input and an output and it goes through a wire. And that's it. So topologically, this is tautology. There are topological tautologies here. And therefore, the sort of non-trivial little thing we try to express here in relating states to processes and vice versa becomes fairly trivial. So, and this is what this is going to be our new type of diagrams where you've got caps and cups like that, which, well, satisfy these equations, but these are not equations we have to remember. These are not equations we have to remember. This basically means well, only topology matters. If you got something which connects a certain input to a certain output, we don't really care how it goes the wire, as long as it goes from an input to an output. Okay? And so this leads us to a definition. Basically, we also have to require these terms out in order to make like the real intuition about a wire. Of course, this would be equal to, and this is actually something you should ask to beside the other equations. So the following are equivalent, this, and this is what we're going to call a string diagram. This is going to be our new type of diagram, or more interesting type of diagram. Actually, we can do better. So basically, I defined a string diagram now as you take these circuits, and then you add a cup and you add a cap, which satisfy to this equation, which satisfy this equation, and satisfy the equation at the bottom here. Actually, you can do much better. And you're basically defining this thing. All the work we just did now is exactly the same as just saying we take diagrams where we can connect inputs to inputs and outputs to outputs. It's the same thing. So obviously, this is what we want. But I just build this up all the way. This is how you would do it the hard way. You sort of add something, you say, okay, now we want a special state and a special effect, and then they behave like that, and then we know that our interesting processes will result in interesting states. Actually, this all boils down to something much simpler. This is equivalent to just saying, well, from now on, an output may be connected to an output, and an output may be connected to an input which is in the back, and an input may be connected to an input. So this is basic. So this is actually just a more liberal kind of diagram. It's actually simpler. You don't really have to say what is it. You don't have to impose the rule, an output has to go to an input in the future. You just drop that rule. So actually you get something simpler. And that's equivalent to all the thing which I've been trying to explain before. So string diagrams is this kind of thing. Why? It's wild. It's wild. Whether it's physically intuitive, ooh, that's another question. But it's simple. Like physically, it's going to cause some weird stuff. Now, going back to like the sort of tensor expressions we have, this is still a sort of an this all carries through with the difference now that you may have. Where is it? Where is an example? Where is the? Yeah, so you can have, for example, that the same index arises both as superscripts, and this means now an output is connected to an output. But sort of symbolic notation just carries through like it did before. And you can start defining interesting notions now. Like, okay, the word transpose, you know, from linear algebra. We can actually define transpose for diagrams too. So we take a box, and we connect its input to an output, and its output to an input. And we call this a transpose. Why do we call this a transpose? We call this a transpose if this would be like a linear map, and this would be a special state, which in quantum theory corresponds to the Bell state, and this is the corresponding effect, and this is effectively the transpose of a linear map. So the inspiration for this definition comes from linear algebra. So that's what a transpose is. But it's in some way, I just said like okay, you connect the input to the output to the input, but you see, if you start analyzing this in terms of a circuit diagram, it's kind of a complex process. You introduce two systems here, you've got an incoming system, you apply a process to the middleman, nothing there, then you do, so it's kind of, operationally, it's a complex, but in diagrammatic terms, totally trivial move. It's a totally trivial move to make. Okay, now, so you can then prove simple maths, like for example, the transpose of a transpose is doing nothing. If we prove it like this, if you do an output to an input, then again to an output, it's trivial, of course. So you get like these little lemmas about transposes kind of for free. Okay, transpose of a cup is a cap, so of course, it's just completely trivial. Now, an interesting thing you can do is actually, it's all about, I don't know whether you get the point, but it's all about notation so far. It's just picking clever notations, clever definitions like string diagrams, and we can actually do the same with transpose. While here it's a definition you have to remember, we again can sort of build the idea of a transpose within the notation. And so this is the new notation. If you take a box, which now for reasons will become clear, I picked asymmetrically, then I will denote it like this. So I take the shape of this box and I rotate it 180 degrees. Why is this a clever notation? Why is this a clever notation? It's a very clever notation that if you pull really hard here down, and you put really hard here up, what happens? It flips like that, right? Or equivalently, if you take this box and you sort of slide it across this wire, it becomes that one. And what remains is just this bit of wire. So it's, again, it's a notation which sort of builds the definition of a transpose inside of the notation. You don't have to remember it anymore.
Doesn't the F become upside down?
Well, we still use keyboards. Yeah. They're sort of dingling. Dangling. Yeah, I know. Actually, I think I once wrote them upside down in one page. It's just horrible. Okay. So I'm not gonna. So you can prove this more symbolically if you don't trust the sort of intuition. Like, so the idea is that you can slide these things down. Of course, this would not have the definition as circuit, but that's clearly the intuition. So anyway, this is symbolic proof. Doesn't really matter because we already showed this anyway. Right. So but again, like if you see something like this, which this is a mathematical equation now, you know. So you've got some rope and there's things on that, so you can actually just slide them all together. And, like, whatever this is, like, it doesn't really matter. It's a mathematical equation. It's a perfectly rigorous mathematical equation. Okay, so other example, trace. You know the trace from linear algebra. This would boil down to this. You get partial trace. So a lot of linear algebraic notions are actually starting to pop out now in these purely diagrammatic terms. Partial trace. And like then if you had a course in linear algebra, they probably made you prove cyclicity of the trace. It's a property of the trace, right? Now, okay, let's see, how do we prove this? F goes to G, G goes to F. F goes to G, G goes to F. Proof. Right? No, you don't have to do any work. Cyclicity of the trace is tautology. Right? They are the same diagrams. Output of G is connected to input of F, output of F is connected to input of G. Same here. They are the same. Now, it's kind of fun. It's kind of fun to do like a Ferris wheel type proof, but it's stupid. It's completely redundant. But you could do this. You could sort of slide first, this one to the other side, and then they rotate. Okay. So that's the intuition of the symbolic proof. We don't even need to do that. The proof is just writing it down. And that's the advantage. Like if you would be doing category theory, then you would be doing this as a proof. But in diagrams, it's just automatic. Right. Okay. Now, in the remainder of the time, I want to show that even at this very general level of string diagrams, we can already start to show things which are kind of quantum-like. And the main idea here is, of course, that a classical state of two systems you would be able to describe by its parts, while a quantum state, this is not the case anymore. And yes, we have this little cup now, which we want to treat as a very special state. This cup, and clearly it's connected, so it doesn't consist of two parts. It's a wire. It's connected. You're not supposed to cut wires or glue wires here. If you do that, you have to leave, because that's the only rule. You can't cut. Yeah.
Well, when you say classical, you mean the properly Boolean world or the probabilistic world?
Not probabilistic.
No,
Not
precisely.
probabilistic, of course. Yeah. Yeah. So we'll distinguish probability and non-probability later. At this moment, it's all pure. It's Boolean world. Yes. Yeah. Of course. Of course. But because it's a good question, because many things people treat as quantum are actually just classic or just probabilistic. So here we've got a theorem. A theorem. Now, given string diagrams, we have now this language of string diagrams, and the idea was to make interesting theories, and we can now show that if all states are separable in our theory, then we got a rubbish theory. So, rubbish is a technical term, which I will define soon, in the context of the proof. So, okay, see, we're just going to prove a lemma, which says that if all states are separable, then all wires are separable. Right? So we take an F here, we just include this little piece of wire here. This thing is supposed to be separable, so we can sort of split it up in two parts, right? And which means that this box is now of this form, right? But if this box is of this form, then even an identity box, an identity wire, would be of this form. So your wires, your identities, are actually not really wires. They're disconnected. So that's a technical notion of rubbish theory. Your wires are disconnected. It's clearly, it's nonsense. If you formalize the idea of a wire and your wires are disconnected, it's like with rubber. It's like if you got like a rubber elastic and you leave it for a few years, it sort of disintegrates. So you're working with a disintegrated rubber theory. So if you make your string diagrams from rubber, then you end up, well, it's time to buy a new one. Right. So, okay, so the idea that you've got correlation, this of course is true in probability theory too, of course. Oh, so many of these things apply to classical probability theory. So if you've got two parties, and one party applies something here, that's the same as the other one applying the transpose there. Right? That's sort of an operation interpretation after this idea of transpose. And if you just specialize this to a state and effect, it's like if Alex does a measurement here and obtains this effect, then we know that the state of the system at Bob's side is this. That's how you read this. That's how you read this operationally. So you immediately get this idea of correlations between the two parties. Of course, this is true in classical probability theory too, because the diagrams are doing that. Here is something really funky. Like, if you got a diagram here, which is true diagram, we can slide G here, F comes then down there. So here you got a true diagram, and this is sort of what we could call the logical reading of a diagram. Just follow the wires. Just follow the wires. This is supposed to be the counterintuitive physical reading, counterintuitive to the physical reading. The physical reading is like this. Physical reading is you've got a wire, something coming in, then you got a special state, then you encounter G, then you encounter F, something goes away. Now if you look at the other side, it's kind of weird. First you got F and then you got G. So what if you're doing all this and here you decide not to do F? How can they sort of reverse? How can it be reversed there? It doesn't really make sense from a causal perspective. And this is actually the simple type of thing people in the beginning, in the early years of teleportation, were very confused about. It's like as if, like people like Bennett, it's as if information is sent back in time and forward and stuff like that. And it's really this phenomenon. And then very recently, a few people, they did an experiment like this. Basically, they checked something like this, which is like pure quantum mechanics, and they said we realized time travel, and they made it on the cover of the New York Times. Yeah. It's a lie, of course. It's a lie. There is this logical reading, which is a little bit different than physical reading, and that's actually the origin of many of the sort of so-called quantum mysteries. This is actually true for classical probability theory too, by the way. There's nothing quantum about this. Anyway, how much time? But maybe I'm going to skip the proof here. But I'm just going to state what you can do. So basically, one of the key theorems of quantum theory is Nocloning. One of the central theorems of quantum theory is Nocloning, which means that if you've got a state of a quantum system, there is no operation which actually makes two copies of it, if you don't know what it is. So, unlike in a classical computer, you can copy, you buy one song and then you copy it for all your friends. You can't do this with quantum states. And so you can actually prove this already at this level. You can prove this at this level. And what are the assumptions you need? So assume that this is some operation which copies. So this is a very reasonable assumption. If you make two copies, you can swap the copies because they're copies, right? This is a totally trivial assumption. It means there is some state and there is some effect which, if you apply them to them, happen with certainty. It's a completely trivial assumption. And then here is the sort of tricky thing. If you got two copying machines and you got two systems, you would assume that applying my first machine to my first system, my second machine to my second system, that I copy both of them. That's what you would assume from a copying device. Now, assume that you try to copy two systems and they happen to be in such a state. And if you then assume that you got two copies of them, basically everything goes wrong. It's not surprising. If you look at it like this, you sort of feel already, yeah, this is going to go wrong. Because here we've got a diagram which is completely connected, and here we've got a diagram which is disconnected. So you assume it's going to go wrong, and it's going to go wrong. So this is very different than the Nocloning you would find in textbooks. But it's sort of very close to the idea of diagram, you know. I'm not going to give the proof, but it's really just some topological, some manipulations of this rule, and then establish. What you establish again at the end is again that identities are disconnected. So you get again like the rotten rubber theory, if you would have copying operation. It's okay to end. Like within string diagrams, so we got this nice idea of a transpose. So you take a box and then you reflect it, then you make a 180-degree rotation. We're also going to assume now that there exists, for each box, there exists also a flip box. It's just an assumption we make. You can always assume that because you could just take this one to be that one, trivially. But, okay. In many cases, this guy will not be the same as this. For example, in the case of linear algebra, you want this to be the adjoint, which is not equal to the transpose. And then if you compose the adjoint and a transpose, you get a conjugate, component-wise conjugate. So it's the same, assuming that you can conjugate or you can take the adjoint. So we assume this extra level of flipping. And the reason you want to do this is if you work with direct notation, you want to change a ket into a bra. Changing a ket into a bra is not a transpose, it's like the adjoint. And so that's why we will need it to sort of capture the full expressive quantum theory. And then, so okay, I say here we've got this notion of conjugate and adjoint. And then you can, for example, define unitarity. Unitarity means if you compose something with its adjoint, you get identity. You do this at both sides. On one side, they call it isometry. Yeah? So you can define something now. And this brings us to a nice conclusion for this talk. This is quantum teleportation. So sort of something we get now is a very straightforward equation out of our theory. We got a state here, a state psi. Then you see a box we can sort of slide this to the other side. If we assume the equation which you just saw of isometry, unitarity, these two boxes go away, and this actually becomes this. It's a straightforward equation from what we've been developing so far. Physically, this means if Alex, sorry Alex, even with the B. So we got a state here. We perform a certain effect, which is part of a measurement there. So we got a certain effect occurring here. Alice and Bob share a Bell state. If then Bob does a certain operation which is in accordance with this one, then whatever state Alex possessed initially is now at Bob's side. That's quantum teleportation. But you see, like at the core of an equation between string diagrams is completely trivial. Completely trivial thing. And it's interesting to see that like within Hilbert space formalism of quantum mechanics, this took like 60 years to be discovered. Which is a lot. So similar thing. So this is the one which I referred to earlier. Try to write this down on a line, like symbolically, like with direct notation. It just helps. Like what you get here is we got two systems, system A and system B is entangled, system C and system D is entangled. We apply an operation to B and C. Don't care too much about these guys, they are just like local corrections. But by applying an operation to B to C, at the end A and D are in this special state. Although we never touched really A and D together. It's entanglement swapping. It's sort of things which were all discovered in the 90s. And people start to look for things like that. I think that's about, okay, so this is sort of a more dynamic view on teleportation. So you start with you start with a state here, and you share a Bell state. Now you want a state to the other side. It's sort of like a game. How do you do this? How do you do this? Well, it's trivial. You stick a wire, like this is how you do it, right? So this is actually design path. But then you know well, you don't know yet, but we'll see later that in quantum theory you can't do this with certainty, and to actually get a deterministic protocol which you can do with certainty, you have to stick in a possible error which you can then fix at the other side. And that's how actually teleportation works in reality. I think that's it. I stop for here. So now it's up to Jamie. Perfect time.